So I would like to thank the organizers for inviting me to talk about whole systems energy transparency. And in particular, I want to focus on software. I want to give more power to software developers because that will enable them to write cooler programs. And I regard this to be very important in our drive to make and design more energy efficient systems. Now, low power has been the focus of hardware design for more than a decade, and great results have been achieved. But there is evidence that the greatest savings can be obtained at the higher levels of abstraction in the system stack. So the focus is firmly on software, because software ultimately controls what the hardware does. But most software engineers, let's face it, are blissfully unaware of how the decisions they make impact on energy and power. If you're lucky, energy and power are secondary design goals in a software development process. But that doesn't get us away from the fact that the biggest savings can be gained from optimizations at the higher levels of abstraction, and that includes software. And by that I mean algorithms, coding, data types, and data structures. And at the moment, it is very often the case that the great savings that have been achieved for low-power hardware design are effectively wasted by software that doesn't manage the hardware properly and doesn't use the features that hardware designers have painfully put in. And that is because software developers don't know how much things cost. And what I don't see, I can't optimize. If I can't measure it, if I can't see it, I can't optimize it. And energy transparency is the principle, the fundamental concept that tries to bridge that gap. Energy transparency promotes the concept of information on energy consumption being available for programs at a variety of abstraction levels, from machine code to high-level application code, and ideally without costing anything. That means without running the program. Now, we know that transparency as a concept works, and it helps us make more informed decisions in other parts of life. Here is a particularly nice example. That's the back of a rail ticket in Italy, and that gives us information on the CO2 emissions of different modes of transport to different destinations. So really, it's not just a single value that we want, but we want an energy consumption function. And if we had this energy transparency, that would allow us to gain deeper understanding of how algorithms, coding, data encoding, data structures impact on the energy consumed by the program when you run it. Now, the first step towards gaining this understanding and towards energy transparency is to be able to measure energy consumption. And I think there's the first showstopper when it comes to the software engineering community, because measuring energy consumption in most cases these days means that you have to modify the hardware. And that means you have to take to the soldering iron. And while soldering is easy, it is still not part of a software engineering degree. So what we've done is to design our own energy consumption monitoring board. You can download the schematics from majid.org, or you can go and buy one. So that should no longer be a showstopper. We should be able to measure energy consumption even if we are from the software community. Now, if you can do this, then you can start monitoring energy consumption of programs as they run. And that's exactly what this group of second-year students have done as their second-year software development projects. They developed an energy-aware computing framework, effectively an API, that takes energy consumption data from data providers such as the CPU, battery, or the hard drive, and through the API makes this information available to software that might want to make energy-aware decisions, such as an email client or a web browser. And with this API in place, you can then start collecting data about your programs and investigate this data. So the students decided to sort integers between 0 and 255, and these they encoded using 8, 16, 32, or 64-bit unsigned integers. They've looked at a variety of sorting algorithms from different complexity classes and recorded the total time taken for sorting a number of elements, the total energy, and the average power. And now, just to pick one thing out, it's interesting to see that sorting 64-bit values takes less time than sorting 8-bit values. Right? So these are the 8-bit values, that's the time. The 64-bit values take less time. Yet more energy is consumed in the process of sorting the 64-bit values compared to the 8-bit values. Why is that?
64-bit machine and loading addresses across a 64-bit architecture.
Very good. So it's the weight of the data bus, right? It's the weight of the data bus. But without energy transparency, we wouldn't have known, right? So that is the point about energy transparency. It allows us to see things that we previously didn't even know about. If you want to use EACOF, or if you want to contribute, it's all open source. Okay, so that gets me to the topic of static analysis for energy consumption. So far we've measured, we've monitored, but can we do better? Can we actually determine the energy consumed by a program without running it? And we've run a 3-year European-funded project under the name of ENTRA, Whole Systems Energy Transparency. And there we use static resource analysis. So just as a small recap, static resource analysis for energy consumption, we used standard resource usage bound analysis techniques, which date back to a seminal paper from 1975 on resource consumption. We adopted this for energy. These techniques infer upper and lower bounds on energy usage of a program, and these bounds are expressed as monotonic arithmetic functions per procedure, potentially parameterized by the program's input size or other parameters that the program uses. Now, imagine you have a specification of an upper bound and a lower bound for resource usage. So that's your resource, that's the input data size, for instance. And then you write your program, you compile it, and as part of the compilation process, there's an analysis going on, and this analysis gives you an upper and a lower bound as well. Now, with these two results present, you can now do verification by statically checking whether the program meets the specification, under which conditions it doesn't meet the specification, and where you can't be sure. Okay? So that is the beauty of static analysis in this context. Let's use a small example of static analysis in terms of determining resource usage. So here's a small program, a factorial function. And if I want to know how much it costs to run this, then I've got the cost of the comparison plus the cost of this first return, provided that x is less or equal to 0. If, however, x is greater than 0, then I still got the cost of the comparison plus the cost of this return. So that's the comparison, that's the other return. And the cost of this return is the cost of the multiplication plus the cost of the recursive call. Okay, so that's really very simple. And all we now need to do is to find out the costs of these constants, and then we can determine the energy consumption by solving the extracted cost relations, and then we get an energy consumption function for a call to factorial. Now, it's not actually that simple, because otherwise I'd finish by now. What we need to do is we need to construct energy models that allow us to determine these costs, which gets me to the first ingredient for energy transparency, and that is reasonably accurate energy models. They capture the energy consumption during a computation, and once I've captured this, I can use this to feed this into my static analysis. Now, on a very basic level, if I want to determine the energy consumption of a program, I translate it into a sequence of machine instructions, and then I can determine a base cost for every instruction, and then I multiply this with the number of times this instruction is executed whilst the program is running. And then I also need to consider how much it costs to switch the circuit state from executing instruction I to instruction J. That's the circuit state overhead. I need to determine this, I need to measure this for all instruction pairs I and J, and then multiply this with the number of times these instructions swap over in a program execution. And then, of course, there's other factors, pipeline stalls, cache misses, etc., that I also need to consider. For a modern multi-threaded processor, there is something else I need to consider. I need to think about how much it costs for the machine to be idle, so do nothing. And in addition to this, I need to also factor in how much concurrency costs. So how much does it cost for several threads to be active at the same time? How many threads? The number of threads usually influences the energy consumed as the program runs. So I also need to consider this. And you can model this with reasonable accuracy. Now, if you do this, and if you measure, then you get to pictures like this. This is a heat map, and it gives us an energy cost model per instruction of the XMOS XCore using 32-bit data. This is sorted by the number of operands the instruction takes. So this is 2 operands, 3 operands, 4, 5, 6 operands. And it is not surprising that the 6 operand instructions, they do the most data crunching, actually consume the most energy. Now, I said this is 32-bit data. Did you know that 8-bit data is a lot cooler? So if you do the same measurement using just 8-bit data, you'll find that the heat map suddenly becomes a lot cooler. And that means if your loop in your program only goes to 10 or 100, don't write int x. An 8-bit data representation might be resulting in much cooler code. Right, so once we've modeled energy consumption, we can then use static analysis to determine how much it costs to run a particular piece of code. And we do this by translating our source code to the set of machine instructions. And for this set of machine instructions, we've got our energy model, 1 cost per instruction. And then we put this into a resource analysis tool that runs a static resource analysis algorithm. And we've already looked at this. So instead of this being the source code, what I'm saying is this is now the machine code. The cost relations are extracted from the machine code. Once these costs are instruction costs, we can use the heat map to determine how much each one costs and also the ones to swap over. And that gives us then an equation that comes out from solving the recurrence equations using off-the-shelf solvers. Okay? And that is what you get for a call to factorial. And what we see here is hardware, execution, the static analysis, and also a simulator, which is slightly underestimating. So we were pretty happy with this result. And we asked ourselves how useful it is to provide this to a programmer based on the machine code. Well, clearly for a programmer it would be much more useful to have this information attached to source code because that's where you make your decisions. But moving away from where we are measuring and modeling risks losing accuracy. So maybe a good interim level is the intermediate representation of the compiler. That's where all the optimizations happen, and if we make this available to the compiler might be able to make more energy efficient choices. Now, this necessitates lifting the energy model that we currently have at the instruction set level up into the LLVM IR. And to do this, we need to use a little trick. Remember, we know how much each machine instruction costs, so this is the output from the compilation. And this is the intermediate representation on the other side. And in order to determine the cost of an intermediate representation component, we need to associate it with the instructions, the machine instructions it created or that are associated with it. And because I know the costs of these, I then sum up the associated machine level instructions and associate that cost with the corresponding LLVM IR instruction in our case. So we do a reverse mapping and we use the debug information in the LLVM IR tools in order to do this. Now, with this in place, instead of doing the analysis at the machine level, I can now lift my energy model from the machine level through this little trick onto the LLVM IR. My resource analysis now extracts the cost relation from the LLVM IR, and I get results at the LLVM IR level. And these results I could make available to the compiler. And that gives me reasonably good results. Right, so to sum up, to achieve energy transparency, we need energy models, and we need analysis techniques for energy consumption. Now, we found that with energy models, there's a lot to ask still at this stage. There's a lot of fundamental research questions, because what I haven't yet admitted is that energy is actually data dependent, and that is very different from time. It is data dependent, and what we see here is the association of a single cost per instruction. Okay? And that was achieved by giving this instruction randomized valid data and then averaging over the measurements observed. Now, if we pick one out, like this one is a subtraction, we subtract operand 2 from operand 1, and this nicely looking green result, which is roughly here, turns into a picture like this. What's happening? Let's have a close look. So if we pick a data value, 128, as long as I subtract from it values which are less, I'm in the blue. As soon as I subtract from it values which are bigger, I'm in the red. That is the impact of 2's complement. Now, it would be pretty useful to know which way you are, because you've got a factor of 10 difference. So that's pretty large in terms of its impact. So that motivated us to look at other instructions. An add instruction, a shift, and the most beautiful is probably the logic AND. We also looked at multiplication. We all know that A times B is the same as B times A, right? But is the energy consumed by doing A times B the same as the energy consumed when I do B times A? And if that was the case, this picture would be symmetrical on this diagonal, and it is not, right? So the energy consumption is different if I switch the factors. So that's an interesting observation. And if you want to read more about this, I invite you to read our recently published paper. Right, so there's fundamental research questions on energy modeling, data dependency, compositionality, and also we need energy models that allow us to conclude something about the safety and tightness of the bounds that the static resource analysis can produce. The analysis techniques themselves, well, static resource analysis works very well for IoT-type systems, predictable architectures. Hybrid profiling-based techniques will work better for architectures which are more complex. So that gets me to my last point, energy-aware software engineering. We know that hardware designers have had the benefit of looking at energy and power as a first-class design goal. Every design effectively is a point in a 2D plane, and you can look at energy always in the context of performance, and you can determine where in your design flow your design is. Software engineers don't have that. What I really want to do is I want to give more power to software developers. I want to write in my code in 5 picojoule do. Okay? And then the compiler tells me yes or no, or perhaps even it tells me yes, provided that your data looks like this. We need new programming models. We need programming models where I can express this, resource awareness in the programming language as a first-class citizen fully embedded into the language. If we had this, we could write cool code for green software. We could, perhaps at a summit like this, have a cool programming competition. We could perhaps in the future have energy-rated software. So what we aim for is promoting energy efficiency to a first-class software design goal, and although we have achieved great results with static analysis, there is still a lot to do. Okay, so these are the people in the group that have achieved all these results. The presentation has all the papers in with links to the actual published papers. I'd like to thank you for your attention.